Okay, let's try this again. So I, last night, tried to go through the notes and fill them in on this video, but the video file got corrupted. So I am just re-recording and kind of explaining my annotations here as we go through these notes. It's a short bit of notes, so hopefully it won't be, these extra explanations won't be too bad. So in this lesson, we're talking about the derivatives and integrals of vector functions, and we're not going over kind of the derivative rules and integration rules that we did in BC calculus. That's kind of a given understanding that you know that now, but we're just clarifying a couple of new things or a couple of rules and how they transfer over to multivariable calculus. So if you'll notice here, the derivative of a vector function here is, you can also define it as a limit, okay, just like we did in BC calculus. We're not going to use this definition very much. It's not as practical here as it is in BC calculus, but I want you to know that this, it kind of indicates that the derivative rules remain the same in this class. If we are going to take the derivative of a vector function that has a different function, f for x, for y, and for z components, assuming they're all differentiable, you take the derivative of each component separately. Okay, all with respect to t, the same variable, but each one independent of each other. We call this derivative the tangent vector, and hopefully that rings some bells back from BC calculus when we were talking about how the derivative of a function is the same value as the slope of the tangent line at a certain point. Okay, so we call r prime of t the tangent vector, and we call it the tangent vector provided that it, one, does exist, okay, at that value, and that it does not equal the zero vector. If we'd like to make it a unit tangent vector, we actually call it something very specific because we'll need this later when we talk about the unit normal vector and the binormal vectors, which we'll get to in a later lesson. But again, a unit vector is a vector divided by its magnitude, so I take r prime divided by its magnitude. Okay, you can add a couple extra symbols here if you would like to make sure that you know that this is magnitude. We call that unit tangent vector kind of big T. So two examples here that are worth mentioning. Okay, one just to kind of get your feet wet in finding the unit tangent vector. So I've given a vector here, and I would like the unit tangent vector specifically at t equals 1. So the first thing I need to do is take the derivative, which I've done here. Okay, don't forget about the power rule. And then if I wanted to find the formula in general, I would stop and take the magnitude of this. But since I want to find it specifically at 1, it's much easier if I plug in t equals 1 first to find r prime of 1. It's the difference between having some complicated formula to take the magnitude of versus taking the magnitude of a numerical vector that we know and it's easy to work with. So when I take the magnitude of this vector, okay, you'll notice that I get square root of 29, which indicates that big T unit tangent vector is equal to 2, negative 3, 4 divided by the square root of 29. Okay, kind of a simple example, but just worth showing one. One other thing I want to show, though, that we did in BC calculus was finding the equation of the tangent line at a certain point. So in multivariable calculus, remember we have different ways to write the equation of a line. We're specifically looking for the parametric equation. Okay, so here I've written that out here, or this is the vector equation. Okay, in the end, we'll separate each component out separately. So the first thing I want to do is I want to find r prime of t. So I take the derivative of each of these functions separately. I get 2t, 2t, and 1. But I need to know the value of the tangent vector at a specific point. If you look here, I've been given an x, y, z, not a t value. So I need to find t, which I've done here. I've set each of these functions equal to the x value, the y value, and the z value, and then solved for t. This one was pretty easy to solve. I could see that if I plugged in t equals 0, I got the numbers that I needed. Okay, so I'm looking for the value of the tangent vector when t equals 0. So I take t equals 0 and plug it in. I get the vector function 0, 0, 1. Since I am not, again, looking for the unit tangent vector, I'm looking for an equation of a tangent line. Okay, I'm splitting them up into each parametric form. Okay, I'm using the initial point, -1, plus the direction vector, which is r prime, 0, t. okay, using the coordinate 1 for y plus the direction vector 0t. And then for z, I'm getting 1 plus the direction vector 1t. Okay, so this is my final answer, the equation of my tangent line at this point. Okay, so we can also, now that we've taken the first derivative, talk about taking the second derivative. Same rules apply. The second derivative, so let me move this, means just take the derivative a second time. Don't forget about the derivative of cosine and sine being kind of cyclical here. Okay, so second derivative, negative cosine t, 0, 6t. With our derivatives, we have a new kind of definition, a new qualification for our curves. We can qualify a curve as smooth if the tangent vector, r prime of t, is continuous, and it is not the 0 vector except maybe at the endpoints. Okay, that's what that means. It cannot be the 0 vector. And let's see what that looks like in the next two examples. So in the first example I have here is my vector function, and I've taken the derivative and gotten e to the t, 2t, 3t squared. If I look at each component on the interval 0 to 1, I know that, well, even on more than the interval 0 to 1, from negative infinity to positive infinity, each of these are continuous either because they are exponential or because they are some kind of polynomial. So I can say that r prime of t is continuous specifically on this interval. If I think about whether or not this function, r prime of t, will be equal to the 0 vector, I need to set each of these components equal to 0. Luckily, e to the t will never equal 0 because it's exponential, so there's no way that each one of these could be equal to 0 at the same exact time. So r prime of t will never be equal to 0 for any value t. Okay, since we know these two conditions, r of t is smooth. If we do the second example, which, a reminder, since this is t ln t, I need to do the product rule. It's been a while since we did that. And don't forget this negative t is still here, which is where I get this negative 1 here. Okay, so I'm looking at this function on the interval 1/2 to 2. And that's important because we have some natural logs here where this function would be undefined. Well, undefined outside this interval, so that's why this interval is important to have started at 1/2. Okay, so if I go ahead and take the derivative, again using the product rule and then simplifying, I get natural log of t, 2t minus 2, e to the t minus 1. One thing I'm going to add here is I want to display to you, let me write this in a different color, okay, that if I am trying to make sure that these are not equal to 0, okay, I'm going to set each of them equal to 0 and make sure that they don't all equal 0 at the same time. So in the first equation, I would get t equals 1. In the second equation, I also get t equals 1. But in the third equation, t would have to equal 0 in order for this to be equal to 0. Since these are not all the same exact time, there is no place on the interval 1/2 to 2 that r prime of t, would be equal to the 0 vector. Okay, so there's no t on this interval that would make r prime of t equal to 0. Remember that the 0 vector means that the vector turns into 0, 0, 0 at the same time, for the same t we plugged in. Okay? Since we also know natural log is continuous from 0 parentheses to infinity, this is continuous everywhere, and this is continuous everywhere. On this interval, this function is continuous, therefore r of t is smooth. Okay, so just checking those two conditions. Some differentiation rules I want to point out. A lot of these are not different, but a couple are worth just kind of mentioning. So here in this first line, I've got u and v are vectors, and if I take the derivative of their sum, I could also take the derivative of them separately and then add them together. Here in this rule, we've got that rule that we're familiar with. If c is a constant, we are also allowed to factor it out before it gets multiplied by the derivative. And 3 through 5 is really where I want to clarify some of these things for you. In 3, f of t is a function and u of t is a vector. Okay, so f of t might just be x or x squared, or excuse me, if we're using t, it would be t or t squared, e to the t, just a function by itself. This is usually a 3 or more component vector. So if I want to do the product rule, okay, the same product rule as before, where I take the derivative of 1, leave the second alone, add the derivative of the second times the first together. So I've also written that out here. Maybe I should add some vector notations for you. But since we don't actually have the multiplication of two vectors, we have to have two new product rules, specifically for the dot product and for the cross product. They work exactly the same, okay? Except that in the dot product, I am multiplying, excuse me, this should have a dot in the middle. Okay, I am dotting these two together. And in the cross product, I am crossing those two together. Okay? All right, these should also have dots in here because the derivative of a vector is another vector. It wouldn't be some kind of constant we can distribute. So let's add some dots in right here. Okay. All right, and then finally, we have the chain rule down here. These have just been a little bit reversed from what we're used to. This is the derivative of the outside function, the vector u, with the function on the inside remaining the same. And then I multiply that by the derivative of the inside. I would usually write these in the reverse order. This just happened to be typed this way. Okay, so our derivative rules are not super different. We just have a few new ones because our definition of multiplication has changed. For integrals, they work the same. So if we want to integrate a function, this is a definite integral, integrate a vector function, I integrate each component separately, and the integral of a vector is still a vector. I have just written it here in linear combination of I, j, and k. Okay, so we integrate each component separately, again, using the same bounds for everybody. This also continues on to show us that the fundamental theorem of calculus is still in existence. So when I integrate a vector and I get a new vector, I will evaluate that top minus bottom, okay, and I will get a vector as my answer. All right, so let's review just a couple of quick rules about integration. Okay, so I've written here, if I'm finding the indefinite integral, I need to, plus c, our favorite thing, is still needs to be added on at the end. So I have a vector here. If I want to integrate this vector with no bounds, indefinite, okay, with respect to t, make sure you're continuing your good notation, I need to integrate each component separately. So I've got 5t, 3t squared, and t to the fourth over 2, plus c. Now c is a vector, because I can't add just one singular constant to a vector. So c is a vector that represents c1, c2, c3, meaning a different c value, maybe they're all the same, who knows, but being added to each component. So this would be our final indefinite answer. You could also leave it here if we're not specifically trying to find each of these c's. If I want to find a definite integral, here's where we're using our fundamental theorem of calculus. Okay, so in this case, I've gone from linear combination form to vector form. Okay, but I've integrated, I've got t squared over 2, t cubed over 3, t to the fourth over 4, evaluated from 0 to 1. Okay, so I plug in the top, 1/2, 1/3, 1/4, minus plug in the bottom, I get the 0 vector. Okay, so my final answer is 1/2, 1/3, 1/4. Okay, one more example, using an initial condition. Okay, so I chose to use my initial condition to solve for c. Excuse me. Okay, you can also remember you can integrate from 0 to t as long as you know you use the correct notation in replacing your variables, and you know how to replace the variables at the end. But here I'm going to use an indefinite integral, and I'm going to integrate, and I say the integral of e to the 2t, oh, a little u sub here, so don't forget your constant on the outside, is 1/2 e to the 2t. The integral of -1 is negative t, and the integral of t squared is t cubed over 3, plus c, because it's an indefinite integral. Here, I'm plugging in r of 0 because that's the initial condition I'm given. If I plug in 0 into this function, I get 1/2 times 1, so I get 1/2, and then 0, 0, plus c. This is supposed to be equal to 1, -1, 0. And here I've shown you a lot of work on how to get here. But if you can think to yourself, what needs to be added to 1/2 to get to 1? and know that in the end you can just get 1/2. What needs to be added to 0 to get to -1, -1, 0 to 0, 0. You don't have to show all of this work as long as you are able to figure out what C1, C2, and C3 should be. So in the end, this is my final answer. My R of t that I was looking for has both the functions I integrated and the added constants. And this one doesn't have one, again, because it was 0. Okay, so just a refresher on some of our integration methods and our rules for integration. I'm going to ask you to go through this new proof on the field notes. It's going to look just like some of the proofs we did, using component by component. Again, your strategy is to expand, combine, and then simplify. Okay, so expand, combine, simplify. That is your general strategy for this. Okay, but this is proving that the derivative of a function times a vector is the function's derivative times the vector plus the function times the vector's derivative. Okay, so we just do it component by component. Notice when we do things component by component, when I am proving something, I am not using a specific function and I am not using a specific vector. That way, our proof is valid for all functions and all vectors that we could ever possibly want to use. So proving something for one specific example is not enough to prove it for all cases, which is why we end up doing this component by component. Okay. All right, that's it.